Today, we're diving into one of humanity's most incredible feats of engineering, flight itself. Every single day, millions of tons of metal lift off the ground and cruise through the air at hundreds of miles per hour. But here's what's truly mind-blowing. Most people think they understand how planes fly, but the real story is far more fascinating than you might imagine. So, how does a 400-ton Boeing 777 actually defy gravity? And why do modern jets have wings that seem almost too small for their massive bodies? In this video, we're going to explore the hidden complexity behind flight in a logical yet simple way. By the end, you'll understand not just how planes fly, but why every single component on a modern aircraft exists for a very specific reason. Now, before we dive into all the moving parts and complex systems, there's one fundamental concept that unlocks everything else in this video. And it all comes down to this: the airfoil. An airfoil is simply the shape of a wing when you slice through it. That distinctive curved shape on top and flatter bottom isn't just for looks. It's the key to understanding flight itself. Here's what's actually happening. When air hits the front of this wing, it splits into two streams. The air going over the curved top has to travel a longer path and speeds up. Meanwhile, the air underneath travels a shorter distance along the flatter bottom surface. Now, here's the crucial part that most people get wrong. It's not just about the speed difference creating lower pressure on top, though that does happen according to Bernoulli's principle. The wing is also actively deflecting that entire mass of air downward. Newton's third law tells us that for every action, there's an equal and opposite reaction. Push air down, and the wing gets pushed up. But here's what makes this truly elegant. Modern aerodynamics combines both of these effects using something called circulation theory. The wing creates a circulation pattern in the air around it, and this circulation directly determines how much lift is generated. This is your key to understanding everything that follows. Every system, every control surface, every design choice on a modern aircraft exists to manipulate, control, or optimize this fundamental airfoil principle. Keep this in mind as we explore how engineers have turned this simple concept into the marvel of modern flight. Now that you understand the airfoil principle, let's see how aircraft designers have built an entire ecosystem of moving parts around it. First, we have the primary control surfaces. These are the pilot's direct tools for manipulating our airfoil principle in real time. The ailerons control roll by creating different amounts of lift on each wing. Move the stick left, the left aileron goes up, reducing lift on that wing, while the right aileron goes down, increasing lift. The plane banks left. It's pure airfoil manipulation. The elevator controls pitch by changing the airfoil behavior of the horizontal tail. Pull back on the controls, the elevator deflects up, creating a downward force on the tail, which pitches the nose up and increases the wing's angle of attack, generating more lift. But here's where it gets really clever. Modern jets spend most of their time cruising at high speeds, where efficiency matters most. The problem? Those sleek, efficient wings that work great at 500 miles per hour are terrible at the slow speeds needed for takeoff and landing. So, engineers created high-lift devices, movable parts that transform the wing's airfoil shape when needed. Flaps extend from the trailing edge, dramatically increasing the wing's camber. That's the curvature that makes the airfoil work. Simple flaps just hinge down, but sophisticated slotted flaps are far more interesting. When these slotted flaps deploy, they create a gap that channels high-pressure air from below the wing to the low-pressure area above. This energizes what's called the boundary layer, that thin layer of air right next to the wing surface. By keeping this boundary layer energized, the wing can maintain lift at much steeper angles before stalling. At the front of the wing, slats do the same job. They're like little auxiliary airfoils that create slots to re-energize the airflow, allowing the main wing to operate at angles that would normally cause a stall. And here's something fascinating about the engines. Yes, they provide thrust, but their placement creates additional aerodynamic effects. Most modern jets mount their engines below and forward of the wing. This means when you add power, the thrust line creates a nose-up pitching moment, actually helping the wing generate more lift during takeoff. Even fuel storage is part of this system. Those massive wing tanks aren't just for convenience, they're structural elements. The weight of the fuel counteracts the upward bending forces that lift creates on the wing, reducing stress and extending the aircraft's lifespan. Now let's see how all these systems work together in the real world. I want to take you through a complete flight cycle to show you how pilots orchestrate this symphony of airfoil manipulation. We start on the ground with our wing in its high-lift configuration. Flaps and slats are extended, transforming our efficient cruise airfoil into a high-lift, high-drag shape perfect for slow-speed operations. At the beginning of the takeoff roll, we need thrust to significantly exceed drag to accelerate. But here's the critical moment: rotation. The pilot pulls back on the controls, the elevator deflects up, creating downward force on the tail. This pitches the nose up, increasing the wing's angle of attack until lift exceeds weight, and we're airborne. But we can't climb away with flaps and slats deployed. They create too much drag. So, as we accelerate and climb, the pilot gradually retracts these high-lift devices, returning the wing to its clean, efficient airfoil shape. Now we enter cruise flight, and this is where the magic of modern aerodynamics really shines. We're in equilibrium. Lift equals weight, thrust equals drag. But maintaining this balance requires constant tiny adjustments. Here's where fly-by-wire systems take over. Modern aircraft like the Airbus A320 are actually aerodynamically unstable. Without computer assistance, they'd be unflyable. The fly-by-wire computers make hundreds of micro-corrections per second, constantly adjusting control surfaces to maintain stability while giving the aircraft incredible maneuverability. When it's time to turn, we enter the most complex phase of flight dynamics. Banking the aircraft tilts the lift vector, and now we need that total lift to do two jobs: support the aircraft's weight and provide centripetal force for the turn. This means we need more total lift than in straight flight. The pilot increases angle of attack to generate this extra lift, but this also increases the stall speed. Too much angle of attack in a turn, and we could experience an accelerated stall, losing control at a speed that would be perfectly safe in level flight. Now for landing, the most demanding phase for our airfoil systems. As we begin our descent, those high-lift devices come back out, but this time they serve a dual purpose. The flaps don't just increase lift, they also dramatically increase drag, allowing us to descend at a steep angle without gaining speed. During the final approach, spoilers may also deploy. These devices deliberately disrupt the smooth airflow over the wing, reducing lift and increasing drag for precise flight path control. And here's something remarkable about modern systems: flight envelope protection. The computers constantly monitor angle of attack, speed, and load factors. If a pilot inadvertently approaches the aircraft's limits, the system gently intervenes, preventing a stall or structural damage while still allowing the pilot to maintain control. From that first moment of rotation to final touchdown, every single action is about manipulating our fundamental airfoil principle, controlling how air flows over those wing surfaces to generate exactly the right amount of lift, exactly when and where we need it. And there you have it, the hidden complexity behind what seems like a simple concept. What starts with understanding the elegant physics of an airfoil becomes an intricate dance of mechanical systems, computer control, and pilot skill. The next time you're sitting in an airliner, remember that you're experiencing the result of decades of engineering refinement. Every control surface adjustment, every flap extension, every computer correction is part of a sophisticated system designed around that fundamental principle of manipulating airflow over a curved surface. From the Wright brothers' first flight to today's fly-by-wire marvels, it's all been about perfecting our understanding and control of the airfoil. And honestly, I find that more amazing than magic. Thanks for flying with Runway Reveals today. If this deep dive into flight physics sparked your curiosity, make sure to like this video and subscribe for more engineering stories that reveal the incredible complexity hiding behind everyday marvels. Until next time, keep looking up and wondering how we make the impossible look so effortless.